So, Joe, take it away.
Thank you very much. Okay, so first question to the audience. How many of you were here last year to hear my speech? Okay. All right, returning crew. All right, you're going to like some of the things that have happened. You'll be disappointed with some of the others, okay? Oh, yeah, start now. Okay, and I'm going to try and make my watch work to do this whole presentation, but, you know, it's new tech, so good luck with that. Oh, wakey. Okay, so recap for those who were here before, and for those who are new, this was the plan. We were going to design and build the satellite. We're going to launch it, fame and fortune await, right? Again, I'm a recovering rocket scientist. Okay, the reality. Come on. Integrating hardware and software is hard. Anyone try it? Come on, I know someone, yeah, you know what I'm talking about. It is very, very difficult to integrate hardware and software and get it right. Okay, so while I do use Apple products, and I have kudos for Apple and the way they integrate, yes, it's a closed wall garden, and I don't care for that, but it's hard. Know what you don't know. This is one of the hardest things to get over because you think you know what you're doing, and then you find out you have absolutely no clue what's going on. It will cost more than you think. It will take longer than you plan. Okay? Thank you. Okay, so what are we building? This is my lab. I call it the studio. It's a pretty neat place. And what do we build there? We build these. Yes, this is a satellite. Now, last time I was here, I was showing you the prototype. This is the engineering model. Okay? Its sister ship is in a clean room being assembled this week. Okay? It's happening. It's finally happening. Longer than I expected, but it's finally happening. Okay? CPU on this thing is, well, we started with the Intel Edison. Okay? Anybody remember that cute little monstrosity? Okay? Oops, it was discontinued. You're going to hear that a lot. We're currently using the NanoPi Air LTS. It's a pretty decent processor. And we have a nice camera on board. It's 5 megapixel. It's not super great, but we're getting about 250 meters per pixel at 500 kilometers altitude. No, I'm not going to see your house, but I can see what we need to see. This is a test, remember. The idea is use off-the-shelf components, open source software, open source hardware, create a satellite. Inexpensive, but very reliable. Okay? Communications. We originally planned to use a pre-built radio. That didn't work out. We had to construct our own radio. It works at 450 megahertz. If you have an experimental license, you can listen to this. If not, no, sorry. It uses less than a watt of power. Okay, so the screen on my watch uses way more power than the radio we're using to broadcast our images back with. Okay? Just the screen, never mind the rest of it. And we do have a license from the FCC to do this. Solar cells. We were originally going to use these beautiful little Trisol X. They're little tiny solar cells, right? You got to stick a whole bunch of them together on your satellite to get power. It was wonderful. They obsoleted them. I have 6. That's it. Okay, so we switch. We go to what's called a monosolar cell, which is what is on here and what is on the sister ship that's under construction. It's awesome. It's wonderful. We might have a business case to use these things. They're obsoleted. Back to square one. We're also using for power a compressed lithium ion or lithium polymer batteries. Does anybody have a clue as to what that means? I know you know. You helped. Any idea? Okay, well, if you take a li-poly bag battery, like if you take an iPhone and you were to just launch it into space, that battery is going to expand and then explode. We keep it under compression using a system inside the satellite, so it has no room to expand, thus keeping the battery from exploding. It's a novel technique. Nobody had tried it until we successfully flew it on a high-altitude glider, and we've flown it on a mission to suborbital space on Blue Origin. So we know it works. Come on. Okay, demo unit. There is a demo unit. Last year, you guys remember this? This year, I will reiterate, if you want to see what this thing actually does, go to discovery.minicubes.com, and you can see the web server that's running on this hardware. It's not super fancy, but it works. It works enough for what we're trying to do. Okay? So what did we learn in all of this? What did we learn? What did we learn? Okay. Number one, read a lot. Okay? I have some wonderful bedtime stories for you. Analysis and Design of Space Vehicle Flight Control Systems. It's a light read. And we also have Spacecraft Systems Engineering, also a very good book if you want to go to sleep. Okay? You have to read a lot. You have to know how these particular functions work on a spacecraft. It doesn't work like you expect it to. Like, here's a good one for you. In orbital mechanics, did you know that if you accelerate backwards, you go down? But if you go forwards, like you see somebody in front of you, you want to catch up, and you accelerate, you're going up. You actually have to reverse, go backwards, fall down, speed up, come up behind, in front of them, and then attach them. You don't learn that in your basic algebra courses. Just let me tell you that, okay? Okay, get help. You'll recognize some of these names. Teachers in Space, Friendly Electric makes our electronics. Alba Orbital is our launch provider. They're working with us so that we can actually integrate our satellite so it can fly. And W.G. Malden is a water quality specialist, which we'll talk about in a minute. Okay, before I go on, there's other people who are very, very important to this happening, and that's your support crew. These are great people. I work with them all the time. But I can't do this without my support crew, who I'm now going to embarrass because they happen to be sitting right there. I got my wife, I got Nathaniel, who's working on electrical, and Tyler, who's helping with the web. And these folks here are great. If you do not have a support group for whatever project you're working on, get them, okay? They will be the best thing you have ever invested in. Okay, be ready for drama. Okay, notice this is all capital letters. Okay, I'm not kidding, be ready for drama. If you're launching a satellite into space, you have to use this software called Drama, which has two models called Sarah and Oscar, and those tell you what your satellite's going to do. For instance, it looks like a squiggly line that falls off, right? Okay, those are your particular orbital patterns, positive and negative. That's the green, that's the red, and that's what happens to your satellite over a period of 5 years. From top to bottom, we're at 500 kilometers, and then we hit the ground. Okay? So there is this decay rate. We need to have that. You need to be able to model that. You need to show the FAA, the FCC, the ESA, the FBI, the CIA, the OSI, that you are not going to muck up satellite pathways. We're a little tiny. We have no propulsion on board. If I were to hit you with this at 17,500 miles per hour, what damage do you think it will do to the satellite? Well, it'll obliterate it. But what will it do to you? That's more the problem. And when you're dealing with things like the International Space Station, which has human beings on board, which are kind of soft and squishy and like atmosphere, you have to be careful with what you do. Okay? It makes it worse because we're in what's called a sun-synchronous orbit. So imagine the Earth. Ta-da, here's the Earth. Most satellites go this way. Oh no, we're going this way. Okay, so everything that's going in this direction is directly in our path at one point or another. So all of this has to be calculated and approved before you get moving. Lots of fun. Okay? Space is expensive. Okay? I had figured about $50,000 to do all of this. It's actually closer to $100,000. Case in point, this wonderful little frame is made out of a carbon fiber 3D printed material called WinForm XT 2.0. This material is rated for space, and just the frame parts were $350 for this one. Oh, but you can't buy just one, you have to buy 3. Oh, and if you made a mistake with one of the parts, you have to do it all over again. So it gets very expensive very quickly. But it's still fun. How many people have a satellite? Okay. Right now, we're experiencing a shortfall of about $30,000, which we hope to make up. We're almost done. The objective last year was to be able to come here and say, it's in space, here's its beacon, you can listen to it. Yay! Success, fame, and fortune are down the road, right? The reality, our original flight in April was canceled. Then we were moved to August, and that was taken over by a different flight, which was classified, so we couldn't be on it. So now we are in November. Okay? So literally, on Monday, this one and its sister ship will be assembled in a clean room. It will then go through these wonderful tests, the vibration, TVAC, and bakeout. So let's just explain those. A vibration test. The rocket's going to shake as it goes up. Are the screws on this going to come out, like on the James Webb Telescope, and potentially cause other satellites riding with us damage? We need to be able to show that there's not going to be a problem. Okay? TVAC. This is a temperature within a vacuum test. Are you going to melt? The material is rated for over 250 degrees Celsius, and it can survive a temperature difference of 300 degrees from corner to corner. So if one side is freezing, the other side is melting, will it hold together? That's what that test is for. The final test is called a bakeout. Okay? Smile, everybody. There's a camera on board. It's not live. I have to take it off its rails before it will become live, but then it will start taking pictures. Okay? But if the bakeout is to see if I outgas. So if there's anything in the electronics that will cause vapors that could get on the glass and ruin the lenses of not only me, but other satellites, we want to know that too. So we have to bake out all of the weird gases. So this goes into a very specialized chamber, not a vacuum. We weigh it before it goes in, we weigh it when it comes out, and we know how much outgassing we have. And if we have too much, we don't fly. You have to fix it and then try again. Okay? But we're launching, yes, finally, unless they cancel it again. Or they have, okay, this is on Rocket Lab Electron flight number 10. Number 9 is on the launch pad right now. If it launches and everything works perfectly, then we are go. If they have a rapid unplanned disassembly or a failure to reach orbit or a non-event at apogee, we're not going. But we're this close. This close. I can almost taste it. A satellite in space, finally. What can go wrong? See the aforementioned failure to reach orbit. XKCD fans? Upgoer 5, you know what I'm talking about? Look up Upgoer 5. It talks about the Saturn V rocket using the 10 100 most used words on the planet. It's really good. We could have a power failure. Okay, this thing relies on, and yeah, we're about to go live. Ready? 3, 2, 1. The satellite's now on. Okay. This satellite is now booting up. It's a standard Linux boot up, and then every 60 seconds it's going to start taking a picture. Pretty cool, huh? Okay. But what if the power fails? What if the solar panels don't work? What if the battery lines are messed up? What if my wonderful compression technique doesn't actually work this time for some reason, some anomaly? We'd have a power failure. Or worse yet, the entire satellite is working and now it doesn't communicate back to Earth. So now it's just sitting out there, dead in space. Okay, bonus points. It's the world's first 3D printed satellite made out of plastic. I got it to space. If it communicates, great. If it sends a picture back, bonus. Okay? So you have to think of it in terms of where do you consider success to be? All right? And for me, getting it into orbit is success. All right? So why do this? I'm basically blowing through $100,000 of mine and other people's money to put a satellite in space. Why? Why, on this beautiful Earth, would somebody decide to put a satellite into space on their own? It's pretty simple. Water. It's pretty good, huh? Who had coffee this morning here? okay, who had tea, who's just taken their water bottle and gotten some water from the fountain, okay? Do you know where that water was 4 days ago? Anybody? It was somebody else's water or coffee or tea, probably Harrisburg, since they're directly up our water chain. Okay? Come on, Wakey. I know you can do it. I know you can do it. Come on. All right. These three pictures are what water treatment facilities look like in the United States of America. Your water is flowing through that. And after you're done with it, this one on the left, this is a holding tank before it's pumped to a waste treatment facility. We have some of the best water quality on planet Earth, and we still fall way short. We continue to lose water at a rapid rate. Cape Town, South Africa ran out of water. Imagine not being able to shower for a month. That was legally mandated in that city that you could not use water for a shower because they didn't have it. The objective that we are trying to do is to monitor our Earth's resources with these things, using them in a way that's never been done before. Okay? Instead of having big satellites that only see a site once every 15 days, our objective is to be able to fly satellites over the same area, if not daily, hourly. This requires a different way of thinking. You don't build 180-pound, 2-ton satellites to do this kind of thing. You build satellites that are small, light, easily replaceable, and cheap. Then you use data on board with the machine learning, which we all heard about earlier today, to sift through the data and send only the important information back to Earth, so you're not clogging up the airways. Now we can get a better picture of what's going on with our water in near real time. That's the ultimate goal. Okay? We can't do it with the little test satellite. Okay? This is the size we'll be using. Okay? It's 3 times the size of our little one. No, it doesn't have the wings on with the solar panels yet, but we're going to put everything we need to take pictures of the Earth, the objective being a 15 meter per pixel resolution in this space, beam it to another series of satellites that transmit it back to Earth. So now, when we have a rain event north of us, we can see the water swells occurring and prepare our water treatment facilities to handle the influx. We'll be able to see pollution on a scale that's never been seen before. That's the objective. Okay? Now, in between this getting built, I have this little guy, which I'm very proud of. This is more what people think of when they think of satellites these days. This is a 3U CubeSat. Okay? This one is designed as a project. By doing this, I was selected to help build this. This is going to be testing radiation shielding for astronauts as a free-flying satellite, and it launches in April of next year. Again, I was told April last time, so maybe November? We'll see. Okay. So I've been doing a lot of research in this, and it's hard. Ladies and gentlemen, thank you for your attention today. It has been a pleasure, and I will take any and all questions regarding the technology, what I'm doing, or how much this thing actually costs. All right?